So first of all, thank you very much to the organizers. It's a marvelous conference. I'm very much appreciating. It's also a very nice town and a very nice university. I want to speak about moment categories and which I have introduced already a long time ago, and which are very much related to restriction categories of Croquet and Lac. So it's some kind of dual notion. And there are some way of imposing more structure and of understanding better some small categories. Actually, I'm interested in three categories which are very important in algebraic topology. This is the category gamma of Siebel, then the category delta, the simplicial category, and the category theta n of André Joyal. And somehow one can understand these categories a little bit better by using the structure of moment category. So I will give a little introduction to my talk, then I will speak about moment categories, perfect moment categories, strongly cocartesian comonads, and at the end I will talk about Joyal, duality. So actually, the main purpose of my talk is to get a relationship between perfect moment categories and strongly cocartesian comonads. Then, by a strict categorical duality, if you just pass to the opposite category, you can replace a comonad by a monad. Co-Cartesianus will be transformed into Cartesianus, and the strong condition 2. So this is a categorical duality, and then there is work of Clark Barwick, which relates strongly Cartesian monads to what he calls perfect operator categories. And actually I borrowed the term perfect from his notion. And as an example, I will recover somehow the duality between Siebel's category gamma and the category of finite sets and partial maps. Then the duality of André Joyal between the opposite of the simplicial category and the category of what he calls combinatorial one disks. These are just also finite ordinals, but you distinguish the first, the top and the bottom element, and you require the maps to preserve top and bottom elements. And it is somehow surprising that you can find a copy of the dual category of the simplicial category inside itself by taking this top and bottom preserving, the endpoint preserving maps. There is a little degree shift. And you can generalize this duality, which also has been done by André, to a duality between the category theta n and the category of combinatorial n disks. So actually, André defines dn and then abstractly defines theta n as the opposite of dn. So in my talk, I will, so to speak, make the converse. So I will start with theta n and I will recover dn as the opposite of theta n. So what is a moment category? A moment category is a category with a factorization system, orthogonal factorization system, and I call the two parts active and inert. And you have two axioms to be satisfied. Each inert map must admit a unique active retraction. And then the second condition is a little bit more technical. So if you have two active maps, F and G, and the inert map into the domain of F, such that IF equals G, then you have RG equals F, where R is the unique active retraction of I. So just these two axioms suffice to have a good notion of factorization system, if you want. And then you define the moments of an object of the category as those endomorphisms for which the active part is a retraction for the inert part. So these endomorphisms are idempotents which are split. So these are split idempotents. And you call this the set of moments of A, and actually it is easy to show that the set of moments of A is in bijection with the set of inert subobjects of A. But the advantage is that moments you can compose them because these are idempotents. And the most important feature is that you can push forward moments along any morphism of your category. So if you have any morphism in your category, in your moment category, there is a push forward operation, so which I call FO star, which takes a moment of A to a moment of E. And you have three properties. If you push forward a moment, another moment, it's just composition. Then if you push forward along two morphisms, it's factorial. And finally, the most important property is this one. So if you have a moment and a morphism on A, then you can push forward the moment and you get actually F composed with the moment on the target. So this is some kind of twist. And actually you can show that these three properties more or less also can be used to characterize moment categories. And so how you define this push forward operation is just that, so when you have a moment on A, then it is the composite of it is the composite of active and inert. And so you can look at the composition of the inert. So this is the, if you want, the inert subobject which corresponds to the moment. So you compose with F, and you apply the active inert factorization system. This gives you an active map followed by an inert map, and this inert map has a unique active retraction. And this defines the moment on V. So this is the push forward of moments. So you see, you use in an essential way the fact that you have an active inert factorization system.
You asked me at least one example.
Yes, it will come. So the example, just a minute. There are some nice properties which are true. So actually moments compose and they form a so-called left regular band. So this means that you have this relation that if you compose two moments, then it's the same thing as this. This is a so-called Schützenberger relation. It's very known in semi-group theory. And so the three properties imply that you have this factoriality property, and it is not true that pushing forward takes the identity to identity. This is in general. It's only true for active morphisms, and somehow you can characterize active morphisms by this. And a very important property for the sequel is that if F is active, then so if this here is also active, then the outer square here is a push-out square. So you can, in the subcategory of active morphisms. So examples, and that's what motivated me. So one example is the syntax category delta, where active means endpoint preserving, and inert means distance preserving. So the inert subobjects of a finite ordinal are just subsegments, if you want. So subintervals of. So when you consider an ordinal as a linear graph, the inert subobjects are the subintervals of this interval. And the active morphisms are the endpoint preserving morphisms. So this satisfies all the properties of the moment category. And the sequence category gamma, so the objects of sequence category gamma are the finite sets, and the morphisms are given by collections of pairwise disjoint subsets of the target indexed by the elements of the source. You can compose them in a natural way, and here you have also an active inert factorization system where the active maps are those which correspond to subdivisions of the target, partitions of the target, and the inert morphisms correspond to those where all the subsets are singleton. And actually, so the dual of gamma is the category of finite sets and partial maps, and or if you want the category of finite pointed sets and pointed maps. And here, if you look at the active inert factorization system, if you pass to the dual, this gives an inert active factorization system, and this is precisely the one Jacob Lurie uses in his higher algebra book. So that is somehow also a motivation to call this active inert. So another example is when you know the notion of a restriction category of Robin and Steve, then the dual of a restriction category is almost a moment category. What you need is that the restriction idempotents are splitting idempotents. Then you get a moment category. However, a moment category has not the property that the moments, so the idempotents, commute with each other. So with respect to this, a moment category is more general than a restriction category. So it would be very interesting to study the common generalization. So few restriction categories where you allow the idempotents not to commute. And so the dual of the category of finite sets and partial maps. So this is a basic restriction category. Is precisely sequence category gamma. Then there is a notion of Rees product of moment categories. So whenever you have a moment category, you can define the Rees product with the simplex category. So the objects are given by an object of the simplex category, a finite ordinal, and an n tuple of objects of C. And the morphisms are given by a map in the simplex category and a bunch of maps between the objects in the Rees product, and you need the simplicial structure to tell which indices are used. But you can compose very easily these maps, And it is interesting that when I introduced this Ries product, I wasn't aware of the fact that actually this Ries product is indeed a special case of a Ries product which has been introduced by Michael Barr and Charles Wells in an old paper, so for computer scientists actually. So this is a construction which exists already in literature. And so what is important is that the simplex, there is a functor from delta to gamma, which maps a finite ordinal n to the finite set n. And so this was the reason for Siegel to introduce gamma, because of this covariant functor. And you can show that if C is an augmented moment category, then so is the Ries product with delta. And then you can define theta n as the iterated Ries product of the simplex category with itself. And it is again an augmented moment category, so there is a functor from theta n to gamma. And actually, what is important is that this augmentation preserves the moment structure. This means the active inert factorization system. So now, this gives some way of understanding better theta n. This active inert factorization system allows you to understand this category better. And I would just perhaps say that theta n is one of the categories which are used by the program of Martina Rovelli and co-authors, actually for both models. So you can use theta n. Either you look at pre-shifts of theta n with values in spaces. This is the Siegel complete model, or you just look at pre-shifts of theta n with values in sets. With the model structure of Dimitrieva, this gives the other model. So understanding the combinatorics of theta n is really a very important thing to understand infinity in categories. But my purpose here is more modest. It's just understand some of the algebra of theta n. So the inert maps of theta n can be interpreted as maps between n globular sets. And so I just would like to give you some intuitive idea how this works. So actually the objects of theta n, here I take an object of theta 2. So this is 2. So theta 2 is delta with delta. So this is 2, and you see you have now to give 2 ordinals. And you give here the ordinal 2, and here say the ordinal 0. I really give a daily version, but just to make some sense to what is written on the whiteboard. The globular set, the 2 globular set associated to this, is given by the sectors. I think perhaps. So, and here, so these are 0 cells. Yes, no other color, I think. So you have 3 0 cells. Then these correspond to 1 cells, and the edges correspond to the attaching maps. So you have 3 1 cells which you attach to these 2 0 cells, and you have one cell which you attach to these 2 0 cells. And then you have two cells which you attach to these two one cells. So this is an object of theta 2. And this is the two globular pasting, the two graph associated to it. And what is written there is that if you look at theta 2 inert, then this is the full subcategory of two globular cells spanned by these globular two pasting sleeves. One for each two-level tree. And it works for any n. So then, and the inert maps are precisely the globular maps. And then you can prove that theta n is actually the Kleisli category of this for the free forgetful junction between n globular sets and strict n categories. And this means that theta n fully embeds into the category of strict n categories. And actually fully and densely. So both embedding fragments. So now I come to the main topic of my talk. What is a perfect moment category? A perfect moment category is a moment category such that the inclusion of the active part admits a left adjoint, which I denote by bar, such that the unit of the junction is pointwise inert. And actually, gamma, delta, and theta n are perfect moment categories. So I just give you a feeling why this is true. So in gamma, the unit of the reflection is just given by adding a new element and embedding n into n plus 1. In delta, you add two elements, one on the bottom and one on the top, and the embedding is shifting by 1. And for theta n, it just follows because perfectness is stable on the least product. So now you have this junction between the inclusion of the active part and the reflection, and you go. So you can show that because the inclusion is inert, it has a unique active retraction. And this defines a moment on A bar. And actually, active maps with domain A bar are in bijection with general maps with domain A. So you can say that A bar is, and moreover, if you push forward the identity of A along F, it's the same thing as pushing forward the moment omega A along G star. So you can say that you have a moment classifier. And actually, each perfect moment category induces a moment classifier comonad. Now you look the adjunction on the other side, you consider it on the active part, and it defines a comonad where L of A is A bar. The co-multiplication is given by L of eta A, and the co-unit is the unique active retraction of eta A. And you can also easily prove that the category itself may be identified with the co-Kleisli category of this comonad. So somehow perfect moment categories are uniquely determined by the active part together with a comonad on it, which is the classifier comonad. So I have until 11:10.
10 o'clock.
Yeah. So now a composable class of morphisms, I call it stable if it is stable under push-out, and these push-outs exist. And I call a comonad cocartesian with respect to the class R if the naturality squares of the co-unit are cocartesian and the co-unit is pointwise in R. And moreover, the comonad preserves push-outs where one leg is a co-unit. Then the proposition is that the moment classifier comonad is cocartesian, even strongly cocartesian, where R is the class of active retractions. So, what does this mean? So, actually, the co-Clemens category can be represented by morphism from LA to B. So, because it's an active morphism from LA to B, and so in particular, these push-outs exist. So you take a general F from LA to B, and the co-unit. So this push-out exists, and the comonad takes it to a push-out, and this allows you to decompose, to factorize F. So the given F is actually equals to the amount from L of A to B, where here you take the co-multiplication, NF and then epsilon B, and thanks to the fact that this is a cocartesian, it's a push-out, you have factorized F in this way. And this is actually a co-free, co-generic factorization of F. So which means that it is initial in factorizations of this form. And so you can characterize the co-free and co-generic part of by saying that in this push-out, so it's co-free if this here is invertible, and it is co-generic if this here is invertible. And the main theorem is that there is some kind of converse. So we have seen that a perfect moment category gives rise to a strongly cocartesian comonad on the active part, and conversely, if you have a comonad which is strongly cocartesian for some stable class, then the co-Clemens category of this comonad is a moment category, where active means co-free and inert means co-generic. And this is back the single duality, because the moment classifier of gamma gives you by duality the partial map classifier on the category of finite sets, and it also gives you Joyal duality if you work a little bit. And if you use the with product, you get the duality between C10 and Dn. So that's the bibliography. Thank you for your attention.
Some questions?
Finite sets and functions can be given the structure of a moment category. Non-empty finite sets are functions.
I think not, no. It is the total category of a restriction category. I think that's the way I see it. You have rather to use gamma, and if you take gamma active, you get the opposite of your category.
So, if there is no more questions, let us Santiago.